Anyone thought at all about the brain teaser, about the seven dwarfs and the evil prince? No? No, so very good. So we're back to this problem. This is the Bill Gates interview question. The evil prince and the seven dwarfs. So what he's going to do is he's going to line them up in a row like this. And there's going to be a red hat or a green hat on each of their heads. And he's going to ask them for one answer, what is the color of the hat on your head? And the only answer they can give is either red or green. Okay? It's an arbitrary number of each. It could be all red, it could be all green, or anything in between. And it's going to be like this. So this guy will be asked first, and he can see all the ones in front of him. And once he gives his answer, he either lives or not. And then this guy gets to answer, and he, again, gets to see everybody in front of him. And depending on his answer, he lives or not, and so on. And they work their way down the road. Okay? Now let me give you a hint. The answer is you can save 6 of them absolutely for sure, and the 7th you have a 50-50 chance to save.
So you ask them from front to back.
From front to back, yeah. Yeah. So each one can see all the ones in front of him, can't see the ones behind him. Okay? And the only answer you can give is either red or green.
The first one says the color of the hat in front of him.
And you save half that way. If you do that, you'll save half of them. You can do better than that. I'm not going to give you the answer today. I want you to think about it a little more. Friday we'll talk about it and we'll go through the answer. But that only gets half of them. Because you're answering for the color on your head, not the one in front of you. You have to know the color of your hat. And of course, you can't see your own hat. Okay. Any other questions about the problem? Yeah. Nope, nothing. Nothing. Could be 100% green, 100% red, anything in between. You don't know anything. It's all up to that evil prince to decide.
The first guy being asked, can see nobody's hat or can see everybody's?
He sees every. No, try to explain it again. This guy can see everybody. This guy can see everybody in front of him. This guy can see everybody in front of him. Can't see backwards, and you can't see your own hat.
Would you guess the problem, like guess the hat?
There's no guessing involved. The answer is there's no guessing involved. Yeah. Well, it doesn't matter. Let's just say, for sake of definiteness, it's this one who can see all 6 in front of him. And then this guy can see all 5 in front of him. He will be asked second. This guy who can see 4 in front of him gets asked next, and so on. So we're working from bottom to top in that drawing. Correct.
If he says the color in front of him, the next person can't say the same.
And then you save half of them that way. Exactly. Exactly right. You save half of them that way. Because this guy will then answer the color this guy said. It will be correct and it'll save him, but it doesn't help this guy know what color is on his head. And he again has the 50-50 chance. So you can do better than that. So think about it a little bit.
So if one guy says it right or wrong, does everybody get to know that he got it
No,
right or
no,
wrong?
no, I don't know anything. You don't know whether he got it right or wrong.
Okay. So
Nope.
they kill whoever after they're all done.
Yeah. This guy, so for example, this guy says red, okay? They hear the one word red, and then this guy is asked what color is the hat on his head. He doesn't know whether that was right or wrong. He doesn't know if this guy lived or died. All he knows is that that guy said red. It's a neat problem. It's a neat problem. Okay. Okay, Friday I'll give you the answer, or you'll tell me. Okay, so we were in the discussion of beta decay, and I was going through this lengthy, not quite derivation, but a sort of argument as to why beta decay spectra have the shape they do. This was worked out by Enrico Fermi in 1934, okay? So only a few years after the idea of the neutrino was invented, Fermi had developed a complete theory of beta decay, which is still the basis of what we understand today to be true. And so I'm going to go through this part quickly because we saw it the other day. We start from the basic quantum mechanical way you calculate the rate for any process, which is Fermi's golden rule. We calculate a transition rate, which depends on some constants, the square of a matrix element, and a density of states. Okay? And we don't worry so much about how we calculate the matrix element. In fact, we can't calculate it very well. So we're going to use the measured experimental rates to tell us about the nuclear matrix elements. Okay, so we write down the wave functions. I'm going fast because you saw this the other day. We have to calculate this density of final states, how many quantum mechanical states there are after the decay happens. This is straight out of Lilly in the appendix. This is just calculating how many states there are for the electron. Those are denoted with the P's. And for the neutrino, those are denoted with the Q's. Plugging those formulas back into Fermi's golden rule, I get this. This is the thing I don't know how to calculate. And G, this little factor G, which comes out front, is a measure of intrinsically how strong the weak interaction is. So it's a number. And if we called the nuclear force 1, then this is something like 10 to the minus 4. So it's weak compared to the nuclear force. Okay, so now we're going to try to finish up that discussion. And now we have to make use of some relativistic kinematics because the electrons typically have energies on the order of an MeV, and their rest mass energies are half an MeV. And the neutrinos also have kinetic energies on the order of MeV, and their rest mass energy is almost 0. So they're very, very relativistic. So I know that the mass of the neutrino really isn't 0, but compared to the electron mass, it's 10 to the minus 7 or so. So for the point of this calculation, and what Fermi assumed was the neutrino mass was exactly 0. And that means for the neutrino, the relationship between its momentum q and its energy E is just a proportionality constant, which is the speed of light. The total energy in the decay is shared between the electron and the neutrino, and that's then rewritten as EE plus QC, because I'm just saying the neutrino energy is its momentum times the speed of light. And then I can differentiate Q with respect to E, or if you like it the other way, I differentiate E with respect to Q. dE dQ is just C, so dQ dEF is 1 over C. And I plug that back into the expression, and I can now write down a number. The number of electrons as a function of their momentum is proportional to some constant times the square of the momentum of the electron times the square of the momentum of the neutrino. And remember that the momentum of the neutrino, again according to that expression, is just the energy of the neutrino divided by C. And the energy of the neutrino is the Q value for the beta decay minus the portion of the energy the electron carried away. That's what this says. And then I use relativistic kinematics to calculate the kinetic energy of the electron in terms of its momentum and its rest mass energy. And when all is said and done, I get this messy equation down here. For the number of electrons now as a function of their momentum, there's some constants out front. There's a momentum squared, and then there's this expression. And now I rewrite it all in terms of the kinetic energy of the electron rather than mixing momenta and energy. And the point is I now get this expression. The number of electrons as a function of their kinetic energy is some constant times the product of these three terms. And the important point now is not what those three terms are, but to see what happens at the extremes of the spectrum. Remember, the beta decay spectrum I showed you experimentally looks something like that. It starts out at 0. It grows for a while, reaches a maximum, and then goes to 0 again at the endpoint energy. And let's just check to see that this expression has the right properties. So suppose TE equals 0, meaning I have a particular beta decay in which the neutrino carried away all the energy, and just by dumb chance, the electron got none of it. So if TE equals 0, notice that first term, there's a TE squared and a 2TE. That term will be 0 when the kinetic energy of the electron is 0. And since it multiplies everything else, that whole expression will be equal to 0 for TE equals 0. So it has the right property down here. Namely, it goes to 0 when the electron energy goes to 0. And then the second term has the other property we need. Namely, when the kinetic energy of the electron equals the Q value, meaning in that case the electron got all of the energy and the neutrino got nothing, that second term is 0, and again the product will be 0. It goes to 0 there. So this thing has the right functional shape to describe what we see experimentally, namely this continuous distribution of electrons as a function of energy with none with 0 and none with the full decay energy, and a probability distribution for intermediate sharing of the energy between the electron and the neutrino. So that all comes from kinematics. There's really very little nuclear physics in it. It's just a calculation of how many quantum mechanical states there are that can be shared among the neutrino and the electron. Okay? Okay. that may have seemed complicated, but the beta decay theory is even more complicated because in doing what we've done so far, we've neglected several things. First of all, we've neglected the fact that the electron or the positron that comes out of the nucleus has an electric charge, and the nucleus has an electric charge. And just because we're talking about beta decay doesn't mean we can forget about the electromagnetic interaction. So those electrons or positrons feel the electric field produced by the nuclear charge, and that affects the rate at which they come out. And again, you can think of it very classically that the electrons are attracted towards this positively charged nucleus, whereas the positrons are repelled away. That changes the shape of the spectrum of electrons or positrons that you observe relative to what you would have calculated neglecting this effect. And the way this is accommodated in the theory is we include something called the Fermi function. I mean, Fermi was a bright guy. He figured all this out. So there's an additional term that we're going to have to introduce. It's usually written as capital F. And it depends on the Z of the daughter nucleus, because obviously the attraction or repulsion is a function of how many protons there are in that nucleus that's left after the decay. So it's the Z of the daughter. And the effect also depends on what the kinetic energy of the electron is. So this is a complicated function. We're not going to go through the derivations. You're going to look it up when you need it. The other thing that we've neglected in all this is to what extent the nuclear matrix element, that thing I wave my hands at, influences the shape of the beta spectrum. And in principle, it can also affect the shape, above and beyond just the simple kinematic things we talked about. So in general, the expression for the number of electrons as a function, here it's written in terms of momentum. Again, there's the phase space factor we had first. Then there's this Fermi function which multiplies it. And that you can think of as a Coulomb correction, the correction because of this electromagnetic interaction. And then there's another factor over here which has to do with the dependence of the nuclear matrix element. And we'll see in a little bit that it depends on how much angular momentum is being carried away by the electron and the neutrino. So we can take this expression up here and rewrite it this way and solve for this quantity QB minus TE. It's just going to be proportional to the square root of this number divided by these factors. And I'm just talking about decays where that S of P is just 1. Okay? And these are what we end up calling allowed decays. So this thing is just proportional to this thing. And so if I make a plot, of this versus the energy of the electron and plot this quantity, what I get is a straight line if this is an allowed decay. So I measure how many electrons I see as a function of their energy. I divide it by the square of their momentum and this Fermi function that's up there. And I plot it as a function of TE. And that funny beta spectrum that I showed you a minute ago will turn into a straight line. And this is what's called a Fermi-Curie plot after the people who suggested doing it. And this straight line will only be true if we have an allowed decay, which we're going to see in a minute, indicates that the angular momentum that the electron and neutrino carry away is 0. And if we see deviations from that, if we see curvature in it, this is a signature of a forbidden decay. And what you can do experimentally is the number of electrons that you see at very high energies is very small. The number that you see in the middle is higher. So if you measure this, you're not going to have very many events out here. But if for some reason you know it's an allowed type decay and this really should be a straight line, you can fit your data up here and extrapolate and figure out where the endpoint actually is and the total number of events that were emitted. Okay. So to obtain the total decay rate, which is going to be related to the lifetime or the half-life of the nucleus, we have to integrate that thing over all the possible momenta, which means integrating from 0 up to the maximum allowed for the particular decay we're talking about. So we need to know the difference in energy between the parent and daughter nucleus. So we end up with this messy looking expression, and your eyes are glazing over, I know. That's okay. This quantity, the Fermi integral, which is the integral of that capital F thing over all the energies, is something that's tabulated. So we don't calculate that. You need fairly complicated calculations to do those integrals. They've been done. There are tables where you can look them up. And we use the fact that we know how to relate the decay rate and the half-life. And so finally we end up with this relatively simple expression, which is something you might have to use, to calculate this funny product of this f, little f, which is the integral of the capital F, times the measured half-life, and it ends up being the log of 2 times some constants divided by the square of the matrix element. And so what you can sort of see here is that the bigger the nuclear matrix element is, which means the bigger the overlap between the initial and final wave functions is, the smaller this quantity will be and the shorter the half-life will be. Okay? So things that have similar initial and final wave functions, the decays will be fast. Where the wave functions look very different from one another, this quantity will be small and this number will be relatively large. Okay? So there's an inverse correlation between lifetime and the square of the nuclear matrix elements. Going back to this Fermi function, this is an illustration of the effect of the Fermi function on the beta decay spectra. So this is the rate at which the betas are coming out, or the number as a function of the energy of the electrons or positrons. If we neglect the effect of the nuclear charge on the shape of these spectra, you get this dash curve that corresponds to essentially saying that there was no charge in the nucleus. The electrons are attracted to the nucleus, and so that pulls the spectrum back to lower energies, because they're sort of fighting that attraction in order to get out. And so the beta minus spectrum is shoved back towards 0, whereas the positrons are accelerated away, and that spectrum gets pushed out to higher energies. Okay, that's what the Fermi function is doing. And just to show you, these are the kind of calculations that you can look up. This is in Prussen's book, but you can find it in most nuclear physics books. This is just a plot of the Fermi function as a function of Z and E. And so the lower set of curves are for positrons, the upper set of curves are for electrons, and you can see the correction factor depends on the Z of the daughter nucleus. But again, it's just, you'd like to understand qualitatively the effect of these things. And to show you experimentally that it really works this way, what you'd like to find is a case where you have a nucleus that decays both by beta minus decay and beta plus decay with similar decay energies. And copper-64 is a nice example of that. It has a situation where it's part of one of these even A mass parabolas, and you know now that there are 2 parabolas, one for the odd odds, one for the even evens. So the copper is an odd odd, and both even A nuclei on either side of it are at lower energies, and therefore it beta plus decays and beta minus decays. The maximum energy for the beta plus is 653 keV. The maximum for the beta minus is 578 keV. So they're fairly similar in terms of their decay energies. And if you look over here, forget about this part for a minute, these are the spectra of the electrons or positrons that are emitted from copper-64. And you can see that the electron spectrum, essentially peaks at 0 energy, whereas the positron spectrum is pushed further out, exactly as we think in terms of that interaction of the electrons or positrons with the nuclear charge. So you can see the effect is really measured experimentally. It's not just a theoretical idea. We see it experimentally in a few situations like that where you have both decays going on. Okay. Now, I showed you earlier that the range of beta decay half-lives is enormous, from milliseconds to 10 to the 16th years. And so these FT values, this thing which I wrote down a second ago, these things would span an enormous range. And so just to make life a little simpler, we normally take the logarithm of them, the log base 10 of this quantity FT. And this funny thing, this log FT, is often called the comparative half-life. It's a way to compare the decay rates or half-lives of different beta decays. And the smallest of them, the ones which will have the smallest values, are the ones which have the fastest decay rates. And the ones which have the largest values, meaning the largest value of log FT, are the slowest decay rates. Okay? It turns out, experimentally, we see that of all the beta decays observed, the ones which are the fastest turn out to be ones in which the initial and final states are both 0 plus. Okay, and we'll see why this is in a minute. These are a class or a subclass of what we call the loud decays, meaning that the neutrino and the electron carry away 0 orbital angular momentum, but because they're so fast, they're called super allowed. Okay, even faster than normal allowed transitions. And they're always 0 plus to 0 plus. And it turns out experimentally, the value of this log FT is between 3 and 4. It's usually around 3.5. And these numbers for these log FTs are a way we'll use to characterize particular beta decays according to whether they're allowed, super allowed, forbidden, and so on. And so it's important that we measure experimentally what the half-lives are. We need to know the decay energies and the Z's of the nuclei to calculate that F value. And once we have those, we can calculate this log FT. So for example, one of the cases of these super allowed decays is shown here. This is carbon 10. So the stable carbon, you know, has 6 protons and 6 neutrons. This is a neutron-deficient carbon isotope. It's only got 4 neutrons, and that's too few neutrons for the number of protons. So it likes to convert a proton into a neutron to get a more balanced situation here, and that's a positron decay. And it turns out the daughter nucleus, boron 10, has a level scheme that looks like this. The parity of 3 plus. The first excited state is a 1 plus. The next excited state is a 0 plus. And all of the beta decay strength of carbon 10 goes right there. Okay, because that is one of these super allowed decays, and that will be the fastest possible decay that this nucleus can do. Okay, now what's going on here? Okay, I've said several times before that with the energies that are involved in nuclear decays, whether it's gamma decay, beta decay, or alpha decay, we're talking on the order of MeVs. And the nuclear size is femtometers. And so if you go and calculate the angular momentum that a particle that has MeV energies can carry away from such a small object, it's very small compared to h bar. In fact, we'll do the calculation in just a minute. And so we tend to classify decays of any type according to how much angular momentum they carry away. And when we were talking about gamma decay a week or so ago, we classified them in terms of multipolarity, which really meant the angular momentum the photon was carrying away. And similarly, we talk about the same thing here, except what's carrying away the orbital angular momentum now are the neutrino and the electron. And in addition to their orbital angular momentum, the L quantum number, remember the electron and neutrino each have intrinsic spin. Okay? They're both fermions, and so they each have intrinsic spin of a half h bar. And so in addition to the orbital part of the angular momentum, we have to consider the spin part. And so in beta decay, there are two types of decays according to the nature of the spins of the electron and neutrino with respect to each other. So in allowed decays, what we mean by allowed is that L equals 0. So the orbital part of the angular momentum that the neutrino and electron carry away is 0. But there are two possibilities for the relative spins of the electron and neutrino. If by chance they happen to be in opposite directions, so that they pair up to spin 0, that's what's called a Fermi decay, okay, after our friend Enrico. Okay? And what that means in this kind of decay is that the spin part of the angular momentum contributes 0, and the orbital part of the angular momentum also contributes 0. So ultimately what that means is the neutrino and the electron carry away exactly 0 angular momentum of any kind. And so what that says is, in terms of the change of spin from the initial nucleus to the final nucleus, is there can't be any. Okay? Whatever the initial spin of the nucleus was, the only final spin which is possible, if it's a Fermi allowed decay, is the same spin. So delta I is 0 in that case. And the same kind of rule that we had before for deciding on a parity change applies here. Namely, the parity change goes as -1 to the L. And so if the orbital part of the angular momentum that the neutrino and electron are carrying away is 0, -1 to the 0 is +1, so there's no parity change either. So in a allowed Fermi decay, we got no spin change and no parity change. On the other hand, the other possibility is the electron and neutrino go off with their spins in the same direction. I mean, they are different particles, so that's perfectly allowed. The Pauli exclusion principle does not prevent that from happening. We can tell the difference between the electron and the neutrino. How are we going to tell the difference? Electrons have charge, neutrinos don't. In fact, maybe that's the only thing which distinguishes them. It could be that's it. Okay? But in any event, we can tell them apart, so that's allowed. That's what's called a Gamow-Teller decay. And so now, in the allowed decays, that means orbital angular momentum 0, But now we have a spin carried away by the electron and neutrino, which is 1 unit. And so if I ask, if I have a certain initial spin in parity, what is the possible final spin in parity given that my electron and neutrino carry away 1 total unit of angular momentum? Okay? So I can then end up with a spin change of 1, which is what you'd expect, but I can also end up with a spin change of 0. How is that possible? How do I start with an initial spin, spit out something with spin 1, and end up with the same spin? Remember, these are vectors. Okay? They don't have to be aligned. Exactly right. So I can have 1 plus 1 equals 1. I can make an equilateral triangle, for example. Okay? So in the Gamow-Teller decay, I get a spin change of either 0 or 1. And again, no parity change because L is still 0 in these allowed decays. And what we're going to do is end up classifying all beta decays in terms of how much orbital angular momentum they carry away. That will determine the degree of forbiddenness. So L equals 0 will be allowed, L equal 1 is first forbidden, L equals 2 is second forbidden, and so on. And then we'll classify them further in terms of whether it's a Gamow-Teller or a Fermi decay. And we'll see how to do that in a minute. Now, I've already used the word forbidden decay, but forbidden is kind of a misnomer. It doesn't really mean it doesn't happen. It just means it happens more slowly or more rarely than the allowed decays. And the reason for this is what I was alluding to earlier, which is we're going to try to calculate the orbital angular momentum a 1 MeV electron carries away from a typical nucleus. So if I have a 1 MeV electron emitted in beta decay, I calculate its momentum using the relativistic kinematics formulas that were on the board a couple minutes ago. It turns out the momentum is about 1.4 MeV over c. And if I assume I'm emitting it from a typical nucleus, mass 100 or so, let's say, I can calculate the radius from which it must have been emitted. It shouldn't be any bigger than the size of the nucleus. That's about 6 femtometers. And so I can calculate classically then what L should be, which is just Rp. Okay? And I do the arithmetic, and that's 0.04 h-bar. Okay? And remember, the orbital angular momentum is quantized in units of h-bar. And so it's going to be tough to emit 1 unit of h-bar, or 2, or 3, or 7. Doesn't mean it won't happen. It's just very, very unlikely. Whereas it's relatively easy to emit 0. Okay? And that's just to show you that in terms of the things we've talked about so far, it's not a surprise that orbital angular momentum 0 is the most likely kind of emission we're going to get. Whether it be betas or alphas or gammas, that's always going to be true. Okay. So let's consider first now allowed decays and try to think of what's really happening here. So allowed means no orbital angular momentum carried away by the neutrino and electron. In the Fermi decays, because the spins of the neutrino and electron are also paired up, that means no spin change whatsoever, no change in parity, no change in L. So now if I think about the shell model, for example, and I'm going to try to understand what's going on in these beta decays in terms of what we know about the shell model, let's consider first a beta minus decay. So in a beta minus decay, I've got a neutron turning into a proton. And we know from the shell model we can explain or describe quantum mechanically what the wave function looks like in terms of a principal quantum number, an orbital part of the angular momentum, the total angular momentum, which is the vector sum of the orbital part and the spin a half of the neutron, and the z projection of that total angular momentum on some axis. So that's how I would describe the wave function of the neutron. And similarly, I can write down a wave function for the proton in terms of its principal quantum number, L, J, and so on. Since what I'm doing in a Fermi beta decay involves no spin change, no parity change, and no change in L, what I must be doing is converting a neutron in one shell model state into a proton in exactly the same shell model state. I don't have any flexibility, okay, because this decay doesn't do anything in terms of angular momentum. So these kind of decays can only happen where I have a situation where I've got a neutron in a state and an available state in the same quantum mechanical situation for the proton. And normally we don't have situations like that, as you've seen before. So these are not so common that you can have a decay like that. In the Gamow-Teller transition, I've got more possibilities because now I'm spitting out an object, this electron and neutrino, with total spin of 1 unit. And so my change of spin that's allowed in this decay is either 0 or plus or minus 1. Again, no parity change, and no change in L. So again, let's suppose I look at a situation here where I'm in a neutron shell model orbital that looks like this: principal quantum number L, principal quantum number n, orbital angular momentum L, and let's just suppose I'm looking at the J state where J equals L plus a half. Remember, in the shell model, J could either be L plus a half or L minus a half. For this example, I'm just choosing the state where J equals L plus a half. I can have two final outcomes for this Gamow-Teller type decay. I can end up with a neutron going into the same shell model state with no change of spin, because that's allowed. Okay? Or, since I have the possibility of changing the spin by 1 unit, I could go from the state with J equals L plus a half to J equals L minus a half. Okay, so I can actually put the final proton into a different shell model state than the neutron was sitting in, but only if I'm doing a Gamow-Teller transition. Yes? Well, remember, in the shell model, that's not possible, because in the shell model, the only thing we have to make up J is the orbital angular momentum of either the neutron or proton and its intrinsic spin. So in the context of the shell model, you can only have J equals L plus or minus a half. And I'm couching this in terms of a shell model state. I mean, you're quite right. I could spin this thing up, but it wouldn't be an appropriate shell model state. There are other cases you'll see where we're not even going to be talking about single particle shell model orbitals as a way to describe the excited states of the nuclei. For example, if we're talking about vibrational states or rotational states, you know that's not the way to describe them. Okay? So in terms of the shell model, J can only be L plus or minus a half. Okay. So that's the discussion for allowed transitions. And remember, what we mean by allowed is L equals 0. The next order, the next most likely transitions, are what are called first forbidden. And again, it doesn't mean it doesn't happen. It just means they're slower or rarer. And what we mean by first forbidden is that the orbital angular momentum that the electron and neutrino carry away is 1 unit. And again, there are two classifications of them. If the intrinsic spin of the electron and neutrino are paired up to 0, that's still called a Fermi transition. But now L equals 1. So now I can have delta I of 0 or 1, just like before. But remember, I can't add 1 to 0 and get 0. So I can't have a 0 to 0 transition where it's a first forbidden Fermi. Okay? And because the orbital angular momentum change is 1, minus 1 to the L is now negative. So there is a parity change if I'm talking about first forbidden decays. And similarly for the Gamow-Teller first forbidden, L equals 1, but now S equals 1. And so there are 3 possible changes of spin. I can get a delta J, delta I, of 0, 1, or 2, depending on how L and S are aligned with respect to each other. And again, there will be a parity change because L, for this case, is still 1. And similarly, if I go to second forbidden, what I mean by that is L equals 2. The change of spin, in principle, can be 0, 1, 2, 3. But in practice, that won't happen because these are going to be allowed decays. And so in general, you may have a situation where you look at a decay and you say, it could be allowed, it could be first forbidden, it could be second forbidden. The lowest order of forbiddenness is the one which will dominate, just like you saw in the gamma decay discussions when you had several different possible multipolarities that could contribute. It was always the lowest order multipolarity which was dominant. The same is true here. And I'll show you some examples of this in a minute. Okay, so we classify these beta decays in terms of their degree of forbiddenness largely from the log FT values, because those are things we can measure experimentally. So we measure the decay energy by measuring, let's say, the masses of the parent and daughter, or we measure the maximum energy of the beta particle that's emitted. That allows us to calculate that quantity F. We know the Z's of the parent and daughter. That's also needed. And then we measure the half-life, and then we get that quantity T. And so we end up being able to calculate this quantity log FT, the comparative half-life. And if you look at all the known beta decays and just make a histogram of log FT values, it turns out they fall into clusters. It's not a random distribution. There are peaks and valleys in it. And they correspond to these different orders of forbiddenness of the decays. So there is a clump all by themselves with comparative half-lives on the order of log FT of 3.5 to those super allowed decays I mentioned earlier. The next level is somewhere between 4 and 7.5, and those are allowed. First forbiddens between 6 and 9, and so on. And you notice there's a bit of overlap between them. Okay, they're not clearly distinguished from one another. So simply measuring a log FT value will not always allow you to definitively assign what kind of transition it is. You may have to do some additional measurements, like looking in detail about the spins and parities of the states involved. But in general, the lower the log FT, the more allowed it is. The higher the log FT, the more forbidden it is. Okay? And that's, again, just because it's hard for these poor little leptons to carry away much momentum. Okay, let's look at some examples. These are what are called beta decay schemes. You've seen some already, and you're going to see a lot more in the homework and in future exams. So here's a relatively simple one. This is tritium. Tritium's a long-lived radioactive isotope of hydrogen. Its half-life is 12.3 years. It turns out the spin and parity of tritium in its ground state is just the spin of that one odd proton, so it's a half plus. And similarly, in the case of helium-3, the ground state spin is due entirely to the spin of the one odd neutron. That's a typo. That should be a 2, obviously. We'll blame Professor Prusen for that. So it's a one odd neutron, and it also spin a half. So what we have in this decay is a change of spin of 0 units, because the decay goes right from the ground state of tritium to the ground state of helium-3. So delta J is 0, and there's no parity change. And in terms of what we've just said, this is going to be an allowed decay because there's no change of angular momentum, there's no change of parity. All equals 0 in that case. Both Fermi and Gamow-Teller are possibilities, because in the Fermi, we certainly know that there's no change of spin. And in the Gamow-Teller, we could have either a change of spin or not. So both of them are possible. And if we think about it in terms of the shell model, this is the simplest case you can imagine. That neutron is in the 1s½ state, and it's turning into a proton in the 1s½ state. And that's exactly what we said either the Fermi or Gamow-Teller transitions could do for an allowed decay. Okay, we can go up to a slightly more complicated situation. This is scandium-49. I'm picking examples that can be described by shell model states initially. Okay, so here's scandium-49. It beta decays into titanium-49. These odd A nuclei in the middle of the F7 half shell. So what's going on here? In the scandium-49, I've actually got 28 neutrons. Okay, so I've got a full F7 half shell of neutrons, because 8 is the maximum I can put there. One of these neutrons turns into a proton, and I've only got one proton initially in that 1f7 half shell model state, so there's plenty of room for another proton to be created, and that's exactly what happens. So in this decay, an F7 halves neutron turns into an F7 halves proton. Again, no change of spin, no change of parity. Again, it'll be an allowed mixed transition, we would call it. Mixed meaning both Fermi and Gamow-Teller can contribute to that. Let's look at another one. Here's magnesium-29. So magnesium-29 in its ground state has a spin of 3 halves plus. Excuse me. It has a short beta decay half-life. It decays into aluminum-29. And let's look at the decays. So there's a decay in which this 3 halves plus state turns into a 5 halves plus state. That's the level at 3184. And another 5 halves plus state, which is the ground state. Those have relatively low log FT values. So I'd like to think of them as being allowed decays, as well as this one here where there's no spin change. Those are most likely allowed decays. But let's think about what's happening in terms of the shell model. So I'm starting out in magnesium-29. So I've got an even number of protons. They're not making the spin. It's that odd neutron which is making the spin there. And it's a d3 halves orbital in which that odd neutron is initially. If I'm going to end up with aluminum-29, now I've got 13 protons. So now the spin is going to be determined by that odd proton. And if I end up with spin 5 halves, I have to think about how I can do that in terms of the shell model. Well, here I've got a d5 halves orbital. So I can put one of these neutrons into the d5 halves. And so I've taken a d3 halves neutron and turned it into a d5 halves proton. That, if you think about it, that involves converting a neutron to a proton and flipping its spin, flipping its intrinsic spin relative to its orbital angular momentum. So I make a transition from a d3 halves to a d5 halves. Only the Gamow-Teller operator allows that to happen. Because in order to flip that neutron spin, I need to have something carrying away 1 unit of angular momentum, and that's the electron and neutrino in this case. So that's how I can distinguish between a Fermi and Gamow-Teller if I know the initial and final spins of the states that are involved. And the transition to this state, since there's no spin change, could be a mixed transition. That is, it could be Fermi and or Gamow-Teller. Okay, and beta decay schemes get more complicated. This is the decay of a fission product that we'll talk about later. This is bromine 85. So these numbers over on the left are the percentages of the time that the bromine 85 decays to a particular state in the daughter nucleus, which in this case is krypton 85. And let's just consider the decay to the 304.8 keV state. That's this one. Okay? So what's going on here is that we're starting out with a spin in parity of 3 halves minus, and we're going nearly 100% of the time, 96% of the time, to a state of spin in parity 1 half minus. So this is a change of spin of 1 unit, 3 halves to 1 half, parity change. So it will be allowed, that is L equals 0. But since there is a change of spin of 1 unit, it can't be a Fermi allowed decay. It's got to be a Gamow-Teller. And for example, we don't see any decay to the ground state, even though there's more energy available, and therefore you'd think more phase space, the density of states should be higher. That should make the decay more favorable. But the problem there is I'm starting with 3 halves negative parity, going to 9 halves plus. That turns out to be a third forbidden decay, and I would encourage you to go back and convince yourself it is third forbidden, meaning that the electron and neutrino would have to carry away 3 units of orbital angular momentum, and that's hard, so that decay has never been observed. Whereas the decay to the excited state, which is allowed, is the way it almost always decays. Okay? Now here's another example. You've actually seen this before. This is the decay of lutetium-176 into hafnium-176. And you know for nuclei in this kind of mass region that we're not going to be using the shell model to describe the excited states. These are going to be rotational excitations because of this particular mass region. And so you see this nice rotational level scheme of the even nucleus hafnium-176. 0 plus, 2 plus, 4 plus, 6 plus, and so on. And previously, I think what I showed you was the decay of the long-lived naturally occurring lutetium-176, which is the ground state of the nucleus. It has a spin in parity of 7 minus in the ground state of lutetium-176 because it's one of these odd guys. And when I add up the spins of the neutron and proton, one of the possible outcomes is 7 minus. And just by quirky nature of the nuclear interaction, the 7 minus state turns out to be the ground state there. That state decays, but very, very slowly for other nuclear structure reasons. And it decays to states of similar spin. So it's starting out with 7 minus. It's going to decay to the 8 plus and the 6 plus. It does not decay down to the ground state or the 2 plus or 4 plus levels because that would be too big a change of angular momentum. And these are the branching ratios for the decays from the ground state. These are the log FT values, and notice they're enormously big. Okay, remember we were talking about 3.5 or 4 for allowed decays, and these are 19 or 20. Okay, so these are really suppressed decays. And you're going to scratch your head and say, wait a minute, why are they so suppressed? Because the only change of angular momentum is 1 unit. They're only first forbidden. They shouldn't be that big. Hang on, we'll talk about that later. It has to do with other details of the nuclear structure. There is an excited state in lutetium-176. It's 127 keV above the ground state, and its spin in parity is 1 minus. And its decay is shown here, and notice it decays down to the ground state in first excited state. Even though it has even more energy for the decay than the ground state of lutetium, it doesn't decay to these high spin states because again, those would be highly forbidden. That would require lots of angular momentum to be carried away by the electron and neutrino. So the 1 minus level goes down to the first 2 plus into the ground state. And so again, you're going to become experts at predicting, if you saw a level scheme like that, where the beta decays will go on the basis of what kind of decay it is. So here's a little bit more about beta decay schemes and how we use them. These are what are called the Fermi-Curie plots that I told you about earlier. This is zinc 62. So here's the decay of zinc 62. It decays to excited states in the daughter nucleus gallium, 72, zinc 72 decaying to gallium 72. The way these experiments are typically done is you produce the radioactive isotope of interest. If you wanted to see the decay which populated the level at 208 keV, and you wanted to see the betas that accompany that, the way you do the experiment is you produce the zinc 72 and you sandwich it between 2 detectors. You have on one side a gamma ray detector that lets you to pick out this particular gamma ray. And if you see that gamma ray, according to that decay scheme, you know that the beta decay populated that 208 keV level. And then at the same time, you detect the beta that was emitted in coincidence with it, and you measure the number of them as a function of their energy. And you end up getting a spectrum, when you make this Fermi-Curie plot that I talked about, that looks like what's in the, actually it's this panel, the lower energy one, okay? And by fitting the data up here, you can extrapolate and calculate what the endpoint energy is and figure out what the endpoint energy is for that decay to that 208 keV level. And similarly, for the decay to the 161 keV level, you would look for a gamma ray of 145 and measure the betas in coincidence with that, and you would get the upper plot. And the difference in energies between 0.25 MeV and 0.3 MeV better be the difference between these energies, okay? Because energy has to be conserved in these processes, and it is. And the fact that those Fermi-Curie plots are straight lines tells you these are allowed decays. And since we're talking about an even nucleus initially, namely zinc 72, the possible spins and parities of the daughter from an allowed decay are either going to be 0 plus or 1 plus. Okay, and it turns out these are 1 plus levels. Just to show you that, in fact, not all decays are allowed, and we can study them experimentally. So here's a case of yttrium-91. Yttrium-91 ground state has a spin of a half minus. It beta decays almost 100% of the time to the ground state of zirconium-91, which has a spin and parity of 5 halves plus. So this is not an allowed decay. In fact, you tell me what kind of decay that is. What order of forbiddenness and what type of decay is it? So how do you figure this out? Look at the delta J first of all. So what's delta J here? 2. Is there a parity change? Yes. Okay. So I want to get delta J of 2 and a parity change with the minimum amount of orbital angular momentum the electron and neutrino can carry away. How am I going to do that? What L value would I pick? 2. Okay. 2 works in terms of the spin, but what about the parity? No, because the parity change goes as -1 to the L, and if L is 2, -1 to the 2 is plus. So it's not. So now I hear 1. Does that work? Okay, in terms of the parity, yes. -1 to the 1 is minus, so that's fine. But how do I get a spin change of 2 with L equal 1? You can. You can. Because remember, I've got these 2 particles, the electron and neutrino, that each have spin of a half. They could be going off in such a way that their spins are parallel. So the S vector for them is 1, and L equals 1, and they happen to point in the same direction, so that L plus S is 2. So this would be L equals 1, S equals 1. That's going to be a first forbidden Gamow-Teller decay. Gamow-Teller because it requires the electron and neutrino spins to be parallel, and first forbidden because L equals 1. Okay? And when I do the same thing, measure the number of betas as a function of their energy, and make one of these Fermi-Curie plots, I don't get a straight line anymore. Notice it's curved. That curvature is a sign that it's not an allowed decay. And you can make a correction which takes that into account, and then you get the straight line. But the initial Fermi-Curie plot that we talked about has this funny structure. That's a sign of a forbidden decay. And here are some more of them. This is one we've talked about a lot before. This is K40, the thing which is in the bananas you like to eat. Okay, so these are the betas which are going through your body right now because it's inside of all of us. It turns out that's a very forbidden decay. It's a 4 minus to a 0 plus, and so that beta spectrum has a lot of curvature in it. Okay. We're going to stop there for today. This is almost the end of the beta decay story, but there's one more type of beta decay we haven't really talked about in detail, which is electron capture, and that's what we're going to finish up on Friday, and that'll complete the discussion. Okay? See you Friday.